Now next, let us move on to the second principle of mathematical induction. So let's see what does this principle tell us first. Suppose in this case we are assuming that S is the set of integers which contain A. So A is present in A, the set S. That is what we are seeing initially. Next we are saying that suppose this set has the property that n belongs to S whenever every integer is less than n and greater than or equal to A. That means we are talking about that particular integer which is less than n and greater than equal to A, that belongs to S. If this is the condition, if this condition is true, then this n would be a member of this set S, right? If this thing is happening here, then that means the set S would contain every integer which is greater than or equal to A. So it would contain every integer which is greater than or equal to A. So in order to prove this, initially we are assuming that A is a member of S. Then we will prove that there is some integer lying between A and n. If that is there, so this n has to be a member of S. If that is so, then we have the condition that every integer which is greater than or equal to A is also member of S. So this is what this theorem tells us. So how we are going to use this second principle of mathematical induction in order to prove various results? Let's see. In this case, we have to prove the following. The first thing that we have to prove that whatever is the statement that is given to us, that should be true for the given integer A. You could choose the integer A to be anything, right? Then accordingly you will move forward. In the second part, what we do, we assume that the given statement or result that is true for all integers which are greater than or equal to A and less than equal to n. So basically we are saying we have to assume that this thing is true for all the integers which is greater than equal to A and less than n, right? And then we'll use this thing in order to prove that statement is true for n. So that means n has to be a member of S. We have to prove this thing lastly. If we have proved this thing, so we have proved the result for every positive integer, right? So let's see how this thing works and how we can apply the second principle of mathematical induction. So remember, you have studied the fundamental theorem of arithmetic. It tells us that you can write any number n as the product of primes, different primes. Either it is a prime itself, if not you can write it as the product of primes, and this product is unique. So in this part, let's prove the existence portion. That means either the number n that is a prime or it is a product of prime. So this is what we will prove here in this case. So for that, let's start our proof by the first part where we assume A to be 2. In this case, you can assume it anything. So let's assume A as 2. Now we are constructing some set S. What is that set? It is the set of integers which are greater than one thing, and moreover it would contain all those integers which are either prime or product of primes, right? Either they are themselves primes or they could be broken down into product of primes, right? So now you know 2, that is a prime number. So 2 is obviously a member of this set S because we have constructed it to be like this. If that is so, this A is a member of S, 2 is a member of S. So this prove our first part. Now for the second part, what we do, we assume that for some integer n, S contain all integers k such that we have this condition A less than equal to k less than n. So k is lying between A and n, and we assume that for some integer n, S would contain all such k. We are assuming that k is some member of S with this condition, right? This thing we are assuming here. Next, we will prove that n is also a member of S. If that is so, we are done with the proof. The result would be true for every positive integer. So we have to prove n is a member of S. Now two cases could arise. Either n itself is a prime number or it is not, right? So let's discuss both of them. So if n is a prime number, then obviously by definition it would be a member of S. Why? Because S contain all the prime numbers and the numbers which are product of primes. So one thing. So for this case the result is clearly true. If n is not a prime number, in that case can you write n as the product of two numbers such that those two numbers, they are obviously less than n, right? Then only you could write this product. So in this case the number a is greater than 1 and less than n, and b is also greater than 1 and less than n. If that is so, so it is obviously there. So it satisfies this condition also, right? If it satisfies this condition also, so that means both a and b, they are member of S. Why? Because according to the condition that according to this condition that whenever we have any number 2 which is less than equal to k and less than n, so if you have this thing, so you can write this to be 2 less than equal to a less than n. There is no issue because here we have applied the equality also. So that means a follows the condition of part 2. If that is so, then a is a member of S. Similarly for b, b is also a member of S. Now because both a and b, they are members of the set S, that means both of them, either they are prime numbers themselves or they could be written as product of primes. In either case, if they are also written as product of primes or they are prime itself, the number n, what would be this? This is a into b. So if this is prime, if this is prime, then n is a product of prime. If not, you could write it to be a1, a2, a3 and so on, and you can write b1, b2, b3 and so on, where all of them, they are primes. So again n is a product of prime. In both the cases you have n as the product of prime, and according to definition, because S contain all the numbers which are either prime or product of prime, so therefore n would now also belong to the set S, right? So this is how you use the second principle of mathematical induction in order to prove the result. So I hope you understood this video well. Well, that is it for this video. Thank you for watching.